There is something strangely comforting about the smallest things in existence. Not because they are simple, and not because science has already tied them up neatly with a label and a formula, but because the deeper we look, the less ordinary reality begins to feel. Tonight, we are settling into that quiet space between what is known and what is still being worked out, between the clean diagrams in physics textbooks and the lingering sense that the universe may be far more subtle than our explanations usually allow. We are talking about particles, the tiny ingredients of matter and energy, the pieces that supposedly build everything from dust to stars, to your own breathing body right now in the dark. On the surface, this sounds like a topic that should be cold, mechanical, maybe even dry. But the truth is almost the opposite. The world of particles is full of elegance, odd behavior, unanswered questions, and moments where the most advanced scientific models on Earth sound less like final answers and more like precise descriptions of a mystery. So, before we go any deeper, subscribe to Sleepy Tin Foil Hat if this is your kind of late-night journey, and let me know where you're listening from tonight. I always like imagining these conversations drifting out through bedrooms, headphones, long highway drives, quiet apartments, and restless minds scattered across the world. And as we begin, let's do it carefully, the way we always should with subjects like this. Start with the mainstream picture. Understand what science truly says, and only then explore the places where the edges get blurry. The mainstream explanation of particles is already astonishing enough without adding anything extra. According to modern physics, everything around you is made from a small family of fundamental ingredients. At the everyday level, you see solids, liquids, air, skin, metal, wood, clouds, food, and walls. But underneath those familiar categories, matter reduces into atoms, and atoms reduce further into electrons orbiting nuclei made of protons and neutrons, and then deeper still into quarks and other elementary particles, described by what physicists call the Standard Model. That model is one of the most successful scientific frameworks ever built. It predicts behavior with extraordinary accuracy. It helped identify particles before they were directly observed. It explains electromagnetic interactions, nuclear decay, and the intricate dance of fields and forces that shape the material world. In that view, particles are not little marbles bouncing around in empty space the way older illustrations once suggested. They are excitations of underlying fields. In other words, what we call an electron is not just a tiny object, but a ripple in the electron field. And what we call a photon is a ripple in the electromagnetic field. The universe in this picture is less like a box full of separate things, and more like an ocean of invisible structures, whose disturbances appear to us as matter and energy. That alone is enough to keep a person awake at night, or maybe, if considered slowly enough, help them drift off into a deeper kind of wonder. But here is where it begins to get interesting for our purposes. Even in the mainstream picture, particles do not behave in the intuitive way most people expect. Quantum mechanics tells us that before measurement, a particle is described by a spread of possibilities rather than one fixed, definite location. It can behave like a particle in one experiment and like a wave in another. It can tunnel through barriers that, classically speaking, it has no business crossing. Two particles can become entangled in a way that makes their properties linked across enormous distances, not in a way that sends usable messages faster than light, according to standard physics, but still in a way that deeply unsettled even Einstein. This is not fringe material. This is textbook material. The weirdness is not an add-on to physics. The weirdness is physics. And that fact matters, because when people hear alternative perspectives about particles, there is often a tendency to either believe too much or dismiss too quickly. But if we stay grounded, we notice something more subtle. The mainstream account is extremely powerful, but it is not the same thing as a final explanation of reality. It tells us how these systems behave with breathtaking precision. It does not always tell us what they ultimately are in the most intuitive or philosophically satisfying sense. That gap between predictive success and deeper interpretation is where many of the most intriguing questions live. For example, what exactly is a field? Physics uses fields with great success, but if you keep asking what a field is made of, or why reality should consist of fields at all, you quickly reach a point where the answer becomes more mathematical than visual. And maybe that is perfectly fine. Maybe reality is under no obligation to feel intuitive to human brains, shaped for hunting, social bonds, and recognizing faces in the dark. But the discomfort remains. Then there is the question of emptiness. We often imagine empty space as nothing, a blank stage where particles move. Yet modern physics says empty space is not truly empty. It seethes with fluctuations, virtual particles, and background activity. The vacuum is not a void in the common sense meaning of the word. It is more like a restless baseline, a lowest energy state that still contains structure. So one of the first secrets of particles, if we can use that word carefully, is that their story immediately changes our story of emptiness itself. The nothing between things may not be nothing at all. And this is where alternative perspectives start to enter, not as conclusions, but as questions worth holding gently in the mind. If particles are excitations of fields, and if those fields fill all of space, are the particles the true foundation of reality? Or are they more like temporary events happening within something deeper? When we say an electron is fundamental, do we mean truly fundamental, or only fundamental relative to the limits of current measurement? Physics has done this before. Atoms were once thought indivisible. Then they were divided. Protons and neutrons looked fundamental for a while. Then quarks appeared underneath them. So when modern science says certain particles are fundamental, that statement is incredibly useful and evidence-based within the current framework. But history suggests caution. It has often been at the very moment humans feel closest to bedrock that another trapdoor opens beneath our feet. The question is not whether science is wrong in some simplistic way. The question is whether our present map, successful as it is, may still be incomplete in ways that become hard to ignore once you sit with the details long enough. One of those details is the uncomfortable incompleteness of physics itself. The Standard Model works beautifully, but it does not include gravity in the same quantum framework. General relativity explains gravity at the scale of planets, stars, galaxies, and the structure of space-time, while quantum mechanics rules the microscopic domain with dazzling success. Both theories work. Both are supported by mountains of evidence. Yet they do not fit together cleanly. This means that our two greatest descriptions of reality are, in a deep sense, not fully reconciled. That is not a small gap. That is a profound clue. It suggests that the particle story we currently tell may be part of a larger architecture we do not yet fully perceive. Add to that dark matter, which seems to shape galaxies through gravity while remaining invisible and unidentified, and dark energy, which appears tied to the accelerating expansion of the universe, and suddenly, the ordinary version of the cosmos starts to look a lot less ordinary. Most of the universe, as far as we can tell, is made of things we do not directly understand. So when people talk about particle secrets, the grounded response is not to leap into fantasy. It is to recognize that the phrase is not entirely dramatic. There really are secrets here, not because scientists are hiding them, but because nature is. Another pattern worth noticing is how often observation itself appears in the conversation. This is where popular culture tends to go off the rails, so we need to move slowly. In mainstream quantum mechanics, measurement matters because quantum systems evolve according to probabilities until interaction produces definite outcomes in the form we observe. That does not necessarily mean human consciousness magically creates reality. most physicists would reject that oversimplified interpretation. Measurement in physics usually means interaction with a system, apparatus, environment, or process of decoherence, not a mind projecting reality into existence. And yet, even after all the clarifications, something strange remains. Observation, interaction, information, and physical outcome are tangled together more deeply than common sense would have predicted. So a careful speculative question begins to emerge. Is reality fundamentally made of particles, or of relationships, or of information, or of something even stranger from which particles emerge as one visible layer? That question is not pseudoscience. It is the sort of question serious thinkers have asked in different language for generations. The dangerous move is pretending we already know the answer. The useful move is admitting that the question itself may be more important than many people realize. There is also a psychological reason this subject feels so rich at night. The particle world quietly undermines the illusion of solidity. The bed, the room, the walls, the body, the phone in your hand, all of it seems stable and self-evident in daily life. But beneath that level, matter is mostly structured emptiness, held together by interactions, probabilities, and forces that are invisible to direct human senses. Solidity is real at our scale, but it is emergent. It is a result, not the deepest layer. In that sense, particles remind us that reality is not false, but translated. What you experience is a version of the world shaped for survival, while science reveals a deeper level that is less familiar, less intuitive, and perhaps more beautiful. The relaxing part of this, oddly enough, is that it loosens the hard edges of certainty. It suggests that the world is not exhausted by the first explanation, or the 100th, that there are still doors unopened, that mystery survives contact with measurement. And maybe that is why a topic like this can feel soothing rather than disturbing. Not because it gives us control, but because it reminds us we were never standing in a fully known universe to begin with. So as we settle into this series, that is our starting point. The mainstream explanation says particles are fundamental excitations of fields governed by precise laws, and that account has earned enormous respect through experiment and prediction. The alternative perspective does not need to deny any of that. It simply asks whether the current model is the whole story, whether fields themselves rest on something deeper, whether information, geometry, hidden structure, or unknown layers of reality may still be waiting underneath the language we use today. We are not here to force conclusions. We are here to notice patterns, examine gaps, compare explanations, and stay honest about where the known world fades into interpretation. And the deeper we go, the more we may find that the smallest things in existence are not merely tiny components of a larger machine, but clues, quiet, subtle clues, that reality is far stranger, far more elegant, and perhaps far less finished than we were taught to assume. As we continue, it helps to slow things down even further, to gently zoom in not just on particles themselves, but on the strange rules that seem to govern how they behave. Because if part 1 introduced the idea that particles are not quite what they appear to be, part 2 begins to explore how they act in ways that feel almost negotiated, as if reality at its smallest scale is less like a rigid machine and more like a system balancing possibilities until something settles into place. And again, we begin with the mainstream understanding, because the grounded explanation is already more than enough to raise questions on its own. In standard quantum mechanics, a particle is described by something called a wave function, which is essentially a mathematical tool that encodes all the possible states the particle could be in, not where it is, but where it might be, and how likely each possibility is. When no measurement is taking place, the system evolves smoothly. almost like a cloud of probabilities spreading and shifting through time. This is not speculation. This is how quantum systems are modeled and tested in laboratories across the world, with results that match predictions to astonishing precision. But then comes the moment of interaction, what we call measurement, and suddenly that spread of possibilities resolves into one specific outcome. The particle is found here, not there. This value, not that one. And this transition from possibility to actuality is one of the most quietly debated aspects of modern physics. The mainstream view offers several interpretations, each trying to explain what is really happening without contradicting the mathematics. One perspective suggests that the wave function does not physically collapse at all, but that all possible outcomes continue to exist in separate branches of reality, a concept often associated with the many worlds interpretation. Another approach, more traditional, treats the collapse as a real physical process tied to measurement or interaction, even if the exact mechanism remains unclear. Still others try to reformulate the entire framework in ways that avoid collapse altogether, focusing instead on how information flows between systems. None of these interpretations change the experimental predictions. They all describe the same observable behavior, but they tell very different stories about what reality might be doing underneath the equations. And that alone is worth pausing on, because it means that even when physics agrees on the results, it does not fully agree on the underlying picture. So here is where the subtle tension appears. If multiple interpretations can explain the same data, then the data itself may not be enough to uniquely define what reality is. It defines how reality behaves when tested, but not necessarily what reality is in its deepest sense. That leaves room, not for wild conclusions, but for careful curiosity. Because it suggests that the particle story is not just about objects moving through space, but about the relationship between possibility, observation, and outcome. And once you start looking at it that way, certain patterns begin to stand out. One of those patterns is the role of uncertainty. In everyday life, uncertainty usually means lack of knowledge. If you do not know where your keys are, that is uncertainty. But in quantum mechanics, uncertainty is built into the system itself. Even with perfect knowledge of a system's wave function, there are limits to how precisely certain pairs of properties can be known at the same time. Position and momentum, for example, are linked in such a way that increasing precision in one necessarily reduces precision in the other. This is known as the uncertainty principle, and it is not a flaw in measurement tools. It is a fundamental feature of reality as described by current physics. That alone raises an interesting question. If uncertainty is not just ignorance, but structure, then what kind of structure allows for that? Why should the universe be built in a way where exactness is limited at the deepest level? Now, the mainstream answer is mathematical consistency. Quantum systems obey equations that inherently produce these limits, and those equations have been tested again and again. But the deeper why remains open, and this is where a grounded speculative angle begins to form, not as a claim, but as a lens. What if uncertainty is not just a constraint, but a hint? A sign that what we call a particle is not a standalone thing, but a kind of interaction pattern, something that only becomes fully defined under certain conditions. In that sense, a particle might be less like a tiny object and more like a temporary agreement between underlying processes. Again, this is not outside the boundaries of serious discussion. Some interpretations of quantum mechanics lean in this direction, describing particles as relational rather than intrinsic, meaning their properties exist in relation to other systems rather than as fixed internal attributes. And once you start thinking in terms of relationships rather than objects, another strange feature begins to feel less isolated. Quantum entanglement, which we touched on earlier, becomes less of a bizarre exception and more of a natural extension of the framework. When two particles become entangled, their properties are described by a shared wave function. Measuring one instantly determines the state of the other, even if they are separated by large distances. The mainstream explanation is careful here. No usable information travels faster than light, and the correlations only become meaningful when results are compared. But still, the connection itself does not fade with distance. It is not carried through space in the classical sense. It simply exists as part of the system's description. So the question quietly shifts again. If particles can be linked in ways that are not easily described by local interactions, then are we looking at a universe built from separate pieces that occasionally connect, or a universe that is fundamentally interconnected, with separateness emerging only at larger scales? The standard framework does not deny interconnection, but it also does not fully reframe reality around it. It treats entanglement as a property systems can have, not necessarily as the defining feature of everything. But some researchers and philosophers have wondered whether that perspective might eventually change, whether entanglement or something like it could be more central than we currently assume. There is also the question of time, which tends to sit quietly in the background of these discussions, but becomes harder to ignore the deeper you go. In classical physics, time flows in a straightforward direction, and particles move through it in predictable ways. In quantum mechanics, the equations themselves often work just as well forward or backward in time. The asymmetry we experience, the sense of past leading to future, is tied more to thermodynamics and the increase of entropy than to the fundamental equations governing particles. That raises another subtle point. If the underlying rules of particles do not strongly distinguish between past and future, then where exactly does our sense of direction come from? And does that mean the particle level of reality is, in some sense, less anchored to time than our everyday experience suggests? Again, we stay grounded. Physics does not claim that time is an illusion in any simplistic sense. Clocks tick, processes unfold, causes lead to effects in consistent ways at observable scales. But at the deepest level, time may not behave exactly the way we intuitively think it does. And if that is true, then particles, as described by those deeper rules, may not be strictly confined to the kind of timeline we imagine. That is not a conclusion. It is a pressure point in the current understanding, a place where the map is accurate, but perhaps not complete. And so, slowly, a pattern begins to emerge. Not a dramatic revelation, but a quiet accumulation of small tensions. Particles are not solid objects in the classical sense. Their properties are not always definite until interaction occurs. Their behavior is governed by probabilities that reflect something deeper than ignorance. They can become linked in ways that challenge classical ideas of separation. And the framework describing them does not fully align with our intuitive sense of time. Each of these points is accepted within mainstream physics. None of them require stepping outside established science. And yet, when you place them together, the picture they form is not entirely comfortable within the older, simpler idea of a universe made of tiny, independent building blocks moving through empty space. So instead of jumping to an answer, we let the question breathe. What if particles are not the final layer, but a visible layer? What if they are the surface expression of something more continuous, more relational, or more informational than our current language captures? That does not invalidate the standard model. It does not undo the precision of quantum theory. It simply suggests that explanation and understanding are not always the same thing, that knowing how something behaves does not always mean we fully grasp what it is. And as you let that thought settle, as the edges of certainty soften just a little, the subject begins to feel less like a puzzle to solve and more like a landscape to explore. Not in a restless way, but in a calm, observant way. the kind where each answer leads to a slightly better question, and each question opens just enough space to keep curiosity alive without demanding resolution. Because the truth is, the particle world is not finished revealing itself, and perhaps it never will be in the way we expect. And that might not be a flaw. It might be part of what makes it worth returning to again and again, especially in moments like this, when the mind is quiet enough to notice just how much remains open. As we move deeper into this quiet exploration, something subtle begins to shift in how we think about particles. Up to this point, we've treated them as the smallest identifiable pieces of reality, even if their behavior is strange and their nature slightly abstract. But now, a different kind of question starts to take shape, one that has been quietly growing in physics for decades, not as a fringe idea, but as a serious line of inquiry. And that question is this: what if particles are not the most fundamental layer at all, but something that emerges from deeper structures, something more like a pattern than a thing? The mainstream view already gives us a hint in this direction, even if it doesn't fully commit to it. As we touched on earlier, particles are described as excitations of fields. That means the electron, for example, is not a tiny bead floating through space, but a localized vibration in an underlying electron field that exists everywhere. This idea alone changes the picture significantly. Instead of building reality from separate objects, physics begins with continuous fields that fill all of space, and what we call particles are simply the ways those fields can ripple. If you imagine the surface of a calm lake, a particle is not the water itself, but a wave moving across it. The wave has energy, momentum, and measurable effects, but it is not separate from the water. It is the water behaving in a particular way. Now, this is where things begin to deepen. Because if particles are just ripples, then the real question becomes, what are the fields? And more importantly, why do these fields exist at all? The Standard Model describes a collection of fields: electron fields, quark fields, photon fields, and others, and it describes how they interact with incredible accuracy. But it does not fully explain why those fields are there in the first place, or why they have the specific properties they do. Their existence is part of the starting assumption of the model. And this is not unusual in science. Every theory has a foundation it builds from. But when you reach that foundation, the questions do not stop. They simply change direction. This is where a more speculative but still grounded line of thinking begins to form. If particles are excitations of fields, and fields are the underlying structure, then perhaps fields themselves are not the final layer either. Perhaps they emerge from something even more fundamental, something not yet fully described. There are already attempts within physics to move in this direction. Some approaches suggest that space-time itself, the stage on which all particles and fields exist, may not be fundamental, but emergent from deeper relationships. Others explore the idea that information, rather than matter or energy, might be the most basic ingredient of reality. These are not settled theories, and they are not universally accepted, but they are taken seriously enough to be actively researched. And here is where the tone of the discussion becomes especially important. It is very easy, when hearing ideas like this, to drift into dramatic conclusions, to imagine hidden layers of reality that sound more like fiction than physics. But the more grounded approach is quieter. It simply notices that every time we have believed we reach the bottom layer of reality, history has suggested otherwise. So instead of declaring what lies beneath particles, we acknowledge that there may be something, and that the current models, as powerful as they are, may not yet reach all the way down. One of the most intriguing directions in this conversation involves the idea that reality might be more about relationships than objects. In some modern interpretations, particles do not possess properties in isolation. Instead, their properties become meaningful only when they interact with other systems. This is sometimes described as relational physics. In this view, the universe is not made of standalone things, but of interactions, connections, and networks of influence. A particle is not a fixed entity carrying a permanent set of attributes. It is a node in a web of relationships, and what it is depends on how it relates to everything else. If you sit with that idea for a moment, it begins to subtly shift the entire picture, because it suggests that what we perceive as solid, independent objects are actually stable patterns within a much more interconnected system. The stability is real. The patterns are consistent enough to build atoms, molecules, and entire worlds. But underneath that stability, the foundation may be less about things and more about ongoing processes. And this aligns, in a quiet way, with what we already see in quantum behavior. Properties becoming definite through interaction, entanglement linking systems across distance, outcomes depending on context. All of these features begin to look less like isolated quirks and more like hints of a deeper structure that is inherently relational. Another layer to this comes from the ongoing effort to unify quantum mechanics with gravity. As mentioned earlier, our current theories do not fully reconcile these two domains. But some approaches to this problem suggest that space-time itself might emerge from more fundamental building blocks, possibly related to quantum entanglement or other underlying structures. In other words, space might not be the container in which particles exist. It might be something that arises from the relationships between more basic elements. If that idea turns out to be correct, then particles would not just be objects within space. They would be part of the mechanism that gives rise to space in the first place. Again, this is not a conclusion. It is an active area of exploration, filled with competing models and unanswered questions. But it adds another layer to our understanding, because it suggests that the hierarchy we are used to, particles inside atoms, atoms inside matter, matter inside space, might not be as straightforward as it seems. The deeper structure could be organized in a completely different way, one where the familiar categories emerge only at certain scales. There is also the question of simplicity. The laws governing particles are incredibly precise, yet they also contain a surprising number of constants, values that must be measured experimentally and then inserted into the equations. The mass of the electron, the strength of forces, the properties of different particles. These numbers are not currently derived from a deeper principle. They are part of the input. And this raises a quiet but persistent question. Why these values? Why this structure? The standard model describes what happens given these parameters, but it does not fully explain why the parameters are what they are. Some physicists hope that a deeper theory will eventually reduce the number of arbitrary constants, showing that they arise from a more fundamental framework. Others consider the possibility that these values may vary across different regions of a larger multiverse, with our universe being one instance among many. That idea is more speculative and more difficult to test, but it appears in serious discussions as one possible way to explain the apparent fine-tuning of physical laws. And again, the careful approach is not to accept or reject it immediately, but to recognize it as one attempt to address a real question. Why does the particle world have the structure it does? As you let all of this settle, something interesting happens to the original concept of a particle. It begins to lose its sharp edges, not in a confusing way, but in a more nuanced way. A particle is still a useful concept. It still behaves in predictable ways under controlled conditions. But it may not be a fundamental thing in the way we once imagined. It may be a stable pattern within fields, which themselves may be patterns within deeper structures, possibly relational, possibly informational, possibly something we do not yet have the language to describe clearly. And that realization, rather than making the subject more chaotic, can actually make it more calming, because it shifts the goal from trying to pin down a final, unchanging answer to observing a layered system that reveals itself gradually. It becomes less about reaching the bottom and more about understanding how each layer connects to the next. The certainty we lose at the deepest level is replaced by a different kind of clarity, a recognition that the universe is consistent, lawful, and deeply structured, even if the ultimate foundation remains just out of reach. So now, as we rest in this space between explanation and mystery, we can see particles not as the final word, but as part of an ongoing story. A story that has already unfolded through centuries of discovery, from atoms to quarks to quantum fields, and that may continue to unfold into layers we cannot yet fully imagine. And the important thing is not to rush ahead of the evidence, but to stay with the questions, to notice where the edges are, and to allow curiosity to move at its own pace. Because sometimes the most revealing insights are not the ones that arrive suddenly, but the ones that slowly reshape how we see what was already there. As we continue drifting deeper into this quiet examination, there is another layer of the particle story that begins to emerge, one that feels less about what particles are and more about how stable reality manages to exist at all. Because if everything beneath the surface is built from probabilities, fluctuations, and interactions that only settle into definite states under certain conditions, then a natural question follows, one that is rarely asked directly, but sits quietly underneath the entire framework. Why does the world appear so consistent, so reliable, so solid, when its foundation seems anything but? The mainstream explanation for this stability is something known as decoherence, a process that helps bridge the strange behavior of quantum systems with the familiar world we experience. At the smallest scales, particles exist in superpositions, meaning they can occupy multiple possible states at once, described by their wave function. But in the everyday world, we do not see objects existing in multiple places simultaneously. We do not see chairs flickering between positions or walls behaving like waves, and decoherence provides an explanation for this transition. It describes how interactions with the surrounding environment, air molecules, photons, thermal radiation, rapidly spread out the delicate quantum states into a broader system, effectively locking in certain outcomes and suppressing others. In simple terms, the more a system interacts with its environment, the more classical it appears. The strange, fluid possibilities of quantum behavior become averaged out, stabilized, and constrained into the definite reality we observe. This process happens incredibly quickly, far faster than human perception, which is why the macroscopic world feels so stable and predictable. And importantly, decoherence does not require conscious observation. It is a physical process, driven by interaction and information exchange, not awareness or intention. This distinction matters because it keeps the explanation grounded in physics rather than drifting into more speculative territory prematurely. But even with decoherence in place, something interesting remains, because decoherence explains how certain outcomes become stable, but it does not fully explain why one specific outcome is realized over others in any given situation. It tells us why the world looks classical, but not necessarily why it looks this way instead of another equally possible configuration. And so, once again, we find ourselves at a boundary where the equations are clear, the predictions are accurate, but the deeper interpretation leaves room for careful thought. This brings us to another quiet feature of particle physics, one that is easy to overlook because it feels so familiar: repetition. The universe is remarkably consistent. Electrons are identical everywhere. The same particle behaves the same way whether it is in a laboratory on Earth or in a distant galaxy, billions of light years away. This uniformity is not trivial. It is one of the most reliable features of physical law. And yet, if particles are excitations of fields, and if those fields permeate all of space, then this consistency suggests that the underlying structure of reality is itself incredibly uniform. Now, the mainstream view accepts this as a fundamental property. The laws of physics are the same everywhere, and the fields that give rise to particles are uniform across space. But the deeper question remains open. Why should this be the case? Why should the universe not vary from place to place, with different particle properties or different interaction strengths? The fact that it does not, at least as far as we can observe, hints at a level of order that goes beyond simple randomness. It suggests that whatever underlies particles and fields is governed by principles that enforce consistency at a cosmic scale. And this is where a more philosophical but still grounded perspective begins to take shape. If the universe is built from underlying structures that produce consistent, repeatable patterns, then those structures must themselves be stable in a very deep sense, not just locally, but universally. This raises the possibility that the apparent randomness of quantum events exists within a framework that is, at a deeper level, highly ordered. In other words, unpredictability may exist on the surface, while the underlying system remains constrained by rules we do not yet fully understand. Another layer of this discussion involves symmetry, one of the most powerful concepts in physics. Symmetry, in this context, does not just mean visual balance. It refers to the idea that certain transformations, shifting position, rotating orientation, changing reference frames, do not alter the fundamental laws governing a system. These symmetries are deeply embedded in the equations of physics, and they lead directly to conservation laws. For example, the symmetry of physical laws over time leads to the conservation of energy. The symmetry over space leads to the conservation of momentum. Particles themselves are tied to these symmetries in profound ways. In fact, many particles can be understood as manifestations of underlying symmetries in fields. This means that what we perceive as distinct objects may actually be expressions of deeper mathematical structures. The particle is not just a thing, but a reflection of a symmetry being realized in a particular way. And again, this is not speculative in the sense of being outside science. It is part of the mathematical framework that successfully describes particle interactions. But once you notice this, another question naturally follows. If particles are tied to symmetries, then what determines those symmetries? Why does the universe have the specific set of symmetries that it does? Why not a different set, leading to entirely different kinds of particles and interactions? This is not something the current model fully explains. It describes the symmetries we observe, but the origin of those symmetries remains an open question. There is also the subtle role of randomness itself. Quantum mechanics introduces probabilities at a fundamental level. When a radioactive atom decays, the exact moment of decay cannot be predicted with certainty, only the probability over time. This randomness is not due to hidden variables in the traditional sense, at least not within the standard interpretation. It is built into the theory itself. And yet, when we look at large numbers of events, the behavior becomes highly predictable. The randomness averages out into stable patterns. So we are left with an interesting balance. At the smallest scales, events can appear genuinely random. At larger scales, patterns become reliable and structured. This dual nature, randomness within order, raises a quiet question about the nature of reality itself. Is randomness truly fundamental, or is it a reflection of deeper processes that appear random from our current perspective? Some interpretations of quantum mechanics accept randomness as a basic feature of the universe. Others explore the possibility of hidden structures or deterministic layers beneath the probabilistic surface, though these ideas face significant challenges and are not widely accepted in their simplest forms. Still, the presence of this question is important, because it reminds us that even the most well-tested theories leave room for interpretation when it comes to the nature of what is being described. The equations tell us what will happen, but not always why it must happen that way. And as all of this unfolds, slowly and quietly, the image of particles continues to evolve, They are no longer just tiny objects, nor even just ripples in fields, but part of a system that balances probability and stability, randomness and order, interaction and consistency. They exist within a framework that is precise enough to build atoms and galaxies, yet open enough to leave fundamental questions unresolved. There is something almost paradoxical about that. The same system that allows us to predict outcomes with extraordinary accuracy also resists being reduced to a single, simple picture. It is as if reality is both knowable and incomplete at the same time, offering clarity at one level and mystery at another. And perhaps that is where the calmness of this topic comes from. Not from having all the answers, but from recognizing that the questions themselves are stable, recurring, and deeply connected to the structure of the universe. They are not signs of failure, but signs of depth, indications that the more we learn, the more carefully we need to think about what learning actually means. So as you settle into this idea, letting it unfold without rushing toward conclusions, you begin to see particles not as isolated curiosities, but as part of a larger pattern. A pattern that holds together the visible world while hinting, quietly and persistently, that there is more beneath the surface, more structure, more connection, more to understand, and we are still only near the beginning of that exploration. As we continue, the perspective begins to shift again, but this time in a way that feels almost imperceptible at first. Up until now, we've been looking at particles as elements within a system, strange, probabilistic, deeply connected, but still part of a framework we can describe. Now, a quieter question begins to emerge, one that doesn't replace what we've discussed, but gently reframes it. What if the behavior of particles is not just a feature of physical law, but a clue about the limits of how we observe reality itself? This is where the concept of measurement, which we've touched on before, begins to deepen in a more subtle way. In mainstream physics, measurement is an interaction. It involves a system becoming entangled with another system, such as a detector or environment, resulting in a definite outcome. This is a well-established idea, and it avoids the need to bring in anything mystical or undefined. But if we look closely, something interesting happens. Every time we measure a particle, we are not simply revealing a pre-existing property in a passive way. We are participating in a process that defines the outcome in a specific context. This does not mean we are creating reality in a literal sense. The system evolves according to physical laws, regardless of whether we are watching. But it does suggest that what we can know about a particle is inseparable from how we interact with it. The questions we ask, the apparatus we use, the conditions we set, all of these influence the form the answer takes. And this is not a flaw in the system. It is a feature of how quantum-level reality operates. So a careful, grounded question begins to form. If the properties of particles are revealed through interaction, then what does it mean to talk about those properties existing independently of all interaction? Do particles have definite attributes at all times? Or are those attributes only meaningful within specific contexts? This is not a new question. It has been debated for nearly a century, and different interpretations of quantum mechanics offer different answers. But the fact that the question remains open is itself significant. One way to think about this, without drifting into speculation too quickly, is to consider the limits of observation. At large scales, observation feels straightforward. You look at an object, and it appears to have definite properties, regardless of whether you are looking. But at the quantum level, observation is not passive. It involves energy exchange, interaction, and disturbance. You cannot observe a particle without affecting it in some way. This is not just a technical limitation. It is a structural feature of reality at that scale. And this leads to an interesting possibility. What if the indeterminate nature of particles is not just about the particles themselves, but about the relationship between the observer and the observed? not in a mystical sense, but in a physical, measurable sense. The system cannot be fully separated from the context in which it is measured. The observer is not outside the system, but part of the interaction network that produces outcomes. Now, the mainstream view would emphasize that this does not elevate human consciousness to a special role. The observer, in physics, can be any system that interacts with another. A detector, a photon, a molecule. These all qualify as observers in the technical sense. And this grounding is important because it keeps the discussion anchored in physical processes rather than abstract interpretations that go beyond the evidence. But even within that grounded framework, something subtle remains. The idea that properties are not fully independent of interaction suggests that reality, at its deepest level, may not be composed of fixed attributes waiting to be discovered, but of potentialities that become defined through relationships. And if that is the case, then particles are not just building blocks. They are events, moments where possibilities resolve into outcomes under specific conditions. This perspective aligns, in a quiet way, with several modern approaches in physics and philosophy. It does not reject the standard model or quantum mechanics. Instead, it shifts the emphasis from what things are to how they behave in relation to each other. And once that shift happens, the idea of a particle as a standalone object begins to feel less central, replaced by the idea of interactions as the primary reality. Another layer to consider is information. In recent decades, some physicists have explored the idea that information may play a more fundamental role than previously thought. Not information in the everyday sense of messages or data files, but in a deeper sense related to the states and relationships of physical systems. In this view, the behavior of particles can be understood in terms of how information is stored, transferred, and transformed. For example, when a particle interacts with a detector, information about its state becomes encoded in the detector. When particles become entangled, their shared state represents a form of distributed information that cannot be reduced to either particle alone. These are not speculative claims. They are part of how quantum information theory describes physical systems. And this has led some researchers to consider whether information itself might be a foundational aspect of reality, with particles and fields emerging from more basic informational structures. Again, this is not a settled conclusion. It is an active area of research, with multiple competing ideas and ongoing debate. But it adds another dimension to our exploration, because it suggests that the stuff of the universe might not be matter in the traditional sense, but something more abstract, something that gives rise to matter through structured relationships. And this brings us back to a familiar theme, but now with more depth. Each time we try to define particles as the fundamental layer, we encounter something beneath them: fields, symmetries, interactions, information. Each layer explains more, but also opens new questions. And the pattern that emerges is not one of failure, but of depth. The deeper we go, the more reality resists being reduced to a single simple description. There is also a quiet implication here for how we think about knowledge itself. If the properties of particles depend on interaction, and if our observations are always part of that interaction, then our understanding of reality is inherently relational. We are not outside observers looking in. We are participants within the system we are trying to understand. And this does not make knowledge impossible. In fact, the success of physics shows that reliable knowledge is very much achievable. But it does suggest that our descriptions of reality are always tied to the ways we engage with it. This is not a limitation to be frustrated by. It is a feature to be understood. It means that reality is not something we simply uncover in a passive sense. It is something we explore through interaction, through measurement, through carefully designed experiments that reveal patterns under specific conditions. And those patterns, once discovered, are remarkably stable. They allow us to build technologies, predict outcomes, and understand the behavior of the universe with extraordinary precision. But beneath that stability, the deeper structure remains just slightly out of reach, not because it is hidden in a conspiratorial sense, but because each layer of understanding reveals another layer beneath it. And particles, as we now see them, sit somewhere in the middle of that structure, not at the top, not at the bottom, but as one of the levels where the invisible becomes visible, where abstract rules become measurable events. So as you let this settle in, the idea of particles becomes softer, more fluid, less like a final answer and more like a doorway into questions about interaction, observation, information, and the nature of reality itself. And the more gently you hold those questions, the more they seem to expand rather than collapse, opening space for thought without demanding resolution. Because perhaps the most interesting thing about particles is not just what they are, but what they reveal about the limits of what we can know, and the quiet possibility that those limits are not barriers, but invitations to look deeper. As we continue moving deeper into this slow and careful exploration, another idea begins to take shape, one that feels less about individual particles and more about the stage they seem to exist within. Because up to now, we've spoken about particles, fields, interactions, and information as if they are all unfolding inside something we casually call space. But what if that assumption itself deserves a closer look? What if space is not simply the backdrop where particles move, but something that is intimately tied to their existence, or perhaps even something that emerges alongside them? The mainstream view begins with space-time as a foundational element. In modern physics, especially through the work of Albert Einstein and general relativity, space and time are woven together into a single structure that can bend, stretch, and curve in response to energy and mass. This framework has been tested with extraordinary precision, from the motion of planets to the bending of light around massive objects. In this picture, particles exist within space-time, and their interactions are influenced by its geometry. Gravity itself is not treated as a force in the traditional sense, but as the curvature of space-time guiding the motion of matter. At the same time, quantum mechanics operates with its own set of rules, often treating space as a kind of stage where probabilities evolve and interactions occur. And while both frameworks are incredibly successful within their domains, they do not yet fully merge into a single, unified description. This gap is one of the central challenges in modern physics, and it leads to a quiet but profound question. Is space-time truly fundamental, or is it, like particles, something that emerges from a deeper level of reality? Some of the most serious attempts to answer this question suggest that space-time might not be a basic ingredient at all. Instead, it could arise from more fundamental relationships, possibly tied to quantum entanglement or other underlying structures. In these approaches, space is not something that exists independently, waiting to be filled with particles. It is something that takes shape as a result of connections between more basic elements. In other words, distance itself might be a measure of how strongly things are related at a deeper level. This idea may sound abstract at first, but if we approach it slowly, it begins to feel like a natural extension of what we've already discussed. If particles are not isolated objects, but expressions of fields or interactions, and if their properties depend on relationships, then it becomes less surprising that space itself might be tied to those relationships as well. The separation between objects could be less about physical distance in a pre-existing space, and more about the structure of the connections between them. And this is where entanglement quietly returns to the conversation, but in a new role. Instead of being just a strange feature of particle behavior, it becomes a possible clue about the fabric of reality itself. When two particles are entangled, their states are linked in a way that does not seem to depend on the distance between them. The mainstream interpretation maintains that no information is traveling faster than light, and that the correlations only become meaningful when compared. But the existence of these correlations, independent of spatial separation, raises a subtle question. Is space the most fundamental way to describe separation, or is it a secondary feature that emerges from deeper connections? Some theoretical work has explored the possibility that space-time geometry itself might be constructed from patterns of entanglement. In this view, the smooth, continuous space we experience could be an approximation of a more discrete, relational structure at smaller scales. The particles we observe would then be part of this structure, not separate from it. They would not move through space in the traditional sense, but would participate in the very network that gives rise to space. Now, it's important to remain grounded here. These ideas are still under development, and there is no single accepted theory that fully explains how space-time might emerge from quantum processes. Different models approach the problem in different ways, and many details remain unresolved. But the direction itself is significant. It suggests that the familiar picture of particles moving through a fixed background may not be the final story. Another aspect of this discussion involves scale. At the level of everyday experience, space feels continuous and smooth. You can move through it, measure distances, and describe motion with great accuracy. But as we approach extremely small scales, near what is known as the Planck length, some theories suggest that space may no longer behave as a smooth continuum. Instead, it could have a discrete or quantized structure, somewhat like pixels in an image, though not in a simple or directly visualizable way. If this is the case, then particles interacting at these scales would not be moving through a smooth medium, but through a kind of underlying structure that defines what space even is. And this raises another quiet question. If space has a smallest unit or fundamental structure, then what determines that structure? What sets its scale, its properties, its rules? Once again, we find ourselves approaching a boundary where explanation gives way to deeper inquiry. There is also a fascinating interplay between energy, space, and the vacuum itself. As mentioned earlier, what we think of as empty space is not truly empty. It contains fluctuations, background activity, and measurable effects such as vacuum energy. In quantum field theory, the vacuum is the lowest energy state, but it is not a state of nothingness. It is a dynamic baseline, filled with potential. Particles can emerge from this vacuum under certain conditions, and then disappear again, leaving behind measurable traces. This challenges the intuitive idea that particles exist within space as independent entities. Instead, it suggests that both particles and the vacuum are aspects of the same underlying system. The distinction between something and nothing becomes less clear. The vacuum is not the absence of particles. It is a state from which particles can arise. And this again points to a deeper structure where the categories we rely on, object, space, emptiness, are not as sharply defined as they appear at larger scales. As all of this comes together, a new perspective begins to form, slowly and without force. Particles are not just things in space. They are part of a system that includes space itself, possibly even contributing to its structure. The relationships between particles may be more fundamental than the distances between them. And the stage on which everything unfolds may not be a fixed background, but something that emerges alongside the actors. And if that is even partially true, then the idea of a particle becomes even more subtle than before. It is no longer just a ripple in a field. It is part of a network that defines fields, space, and interactions all at once. It is a local expression of a global structure, something that appears distinct at one level, but is inseparable from the whole at another. This does not mean that the everyday world is an illusion. The space around you is real in every practical sense. Distances can be measured. Motion can be described. The stability of the world remains intact. But beneath that stability, the deeper structure may be more interconnected, more relational, and more dynamic than our intuitive picture suggests. And there is something quietly calming about that realization. Not because it simplifies reality, but because it reveals a kind of underlying coherence. Even the strangest features of particle behavior, entanglement, uncertainty, emergence, begin to fit together as parts of a larger pattern. A pattern that we are still in the process of uncovering, step by step, layer by layer. So as you let this idea settle, you can begin to see particles not as isolated points moving through empty space, but as elements within a deeper structure where space itself is part of the story. And that shift, gentle as it is, opens the door to an entirely new way of thinking about reality. One where the smallest things are not just building blocks, but clues to the nature of the stage itself. As we continue, there is a subtle transition that begins to take place, one that doesn't immediately announce itself, but slowly reshapes how everything we've discussed fits together. Up to this point, we've explored particles as excitations, as relationships, as parts of deeper structures, even as participants in the emergence of space itself. But now, a quieter question begins to surface, one that sits just beneath all of these ideas. If particles are not truly independent objects, and if space and interaction are intertwined, then where does individuality in the universe actually come from? Because in our everyday experience, individuality feels obvious. You are separate from the room around you. Objects have boundaries. Things begin and end. But at the level of particles, this sense of separateness becomes far less clear. And the more closely physics examines this, the more it reveals something unexpected. Particles of the same type are fundamentally indistinguishable. Not just similar, but truly identical in every measurable way. An electron here is exactly the same as an electron anywhere else in the universe. There is no hidden label, no subtle variation that allows us to track one specific electron as it moves through time. In fact, the equations of quantum mechanics are built in such a way that swapping two identical particles does not produce a new, distinguishable state. The system remains the same, except for a subtle mathematical property that governs how the wave function behaves. This leads to the classification of particles into categories like fermions and bosons, each following its own set of statistical rules. Now, on the surface, this might seem like a technical detail, something relevant only to advanced physics. But if we slow down and look at it more carefully, it becomes something much deeper. Because it suggests that at the most fundamental level, the universe does not keep track of individual identity in the way we do. The idea of this specific particle versus that specific particle may not exist in the way we intuitively imagine. Instead, what exists are patterns of behavior, governed by consistent rules, without the need for individual labels. This begins to dissolve the classical idea of objects as distinct, trackable entities. Instead of a universe made of countless tiny individuals, we begin to see a universe made of repeating patterns, where identity is less about the individual unit and more about the role it plays within the system. And this is not speculation. It is built into the mathematics that successfully describes particle interactions. But this raises a quiet, intriguing question. If particles themselves do not carry individuality, then where does the individuality we experience come from? How does a world of indistinguishable components give rise to distinct objects, distinct structures, even distinct beings? The mainstream answer lies in complexity and organization. While individual particles may be identical, the arrangements they form can be incredibly varied. Atoms combine into molecules, molecules into structures, structures into systems, and at each level, new properties emerge. These emergent properties create the differences we observe. A rock and a tree are made of similar fundamental particles, but their arrangements produce entirely different behaviors and characteristics. This concept of emergence is one of the most important bridges between particle physics and everyday reality. It explains how simplicity at the smallest scale can give rise to complexity at larger scales. But even here, something interesting remains. Because emergence does not just create complexity, it also creates boundaries. It creates the appearance of separate objects, even though those objects are made of components that are not individually distinct. So once again, a deeper perspective begins to form. What we perceive as individuality may not be a fundamental feature of reality, but an emergent one. It arises from patterns, from organization, from stability within a system that is otherwise fluid and relational at its core. And this connects back, in a quiet way, to the idea of fields and interactions. If particles are excitations of fields, and if those fields are continuous across space, then the boundaries between objects are not absolute. They are regions where certain patterns are more stable or more concentrated. The edge of an object is not a sharp dividing line at the fundamental level. It is a transition, a gradient, where one pattern gives way to another. This is not something we notice in daily life, because at our scale, these transitions are effectively sharp. The stability of matter makes boundaries appear solid and well-defined. But beneath that stability, the distinction between one object and another becomes less rigid. And this leads to another subtle question. If individuality is emergent, then what does that say about the nature of systems that appear highly distinct, like living organisms or conscious beings? Again, we stay grounded. Physics does not claim that consciousness is a particle-level phenomenon, nor does it provide a complete explanation for subjective experience. But it does show that the building blocks of such systems do not carry individuality in themselves. Whatever individuality exists at higher levels must arise from the organization of those building blocks, not from the blocks themselves. There is also a fascinating connection here to the concept of symmetry, which we touched on earlier. The indistinguishability of particles is closely tied to the symmetries of the underlying laws. These symmetries enforce consistency, ensuring that the same rules apply everywhere. But they also remove the need for individuality at the fundamental level. If the laws are the same everywhere and the particles are identical, then the universe operates more like a unified system than a collection of independent pieces. And this brings us back, once again, to the idea of the universe as relational. If individuality is not fundamental, and if particles are indistinguishable, then the primary reality may not be the individual object, but the pattern of relationships that gives rise to what we perceive as objects. The focus shifts from, what is this thing, to, how is this pattern organized and interacting? This does not make the world less real. In fact, it may make it more coherent, because it suggests that the stability and consistency we observe are not accidents, but natural outcomes of a system governed by deep symmetries and interactions. The individuality we experience is real at our level, but it is built on a foundation that is more unified than it appears. And there is something quietly calming about that idea. The sense that beneath the apparent complexity and separation of the world, there is a deeper level where everything follows the same rules, where the same patterns repeat, where the distinction between one part and another becomes less absolute. It does not erase individuality, it reframes it. It places it within a larger context, where being distinct does not require being fundamentally separate. So as you sit with this, letting the idea settle without forcing it into a conclusion, you begin to see particles not as tiny individuals, but as expressions of a deeper uniformity. And from that uniformity, through layers of organization and interaction, the richness of the world emerges. Objects, systems, structures, and everything we experience as separate, And yet, beneath it all, the same patterns continue, quietly repeating, holding the entire system together in ways that are both precise and still not fully understood. As we continue, the direction of the exploration begins to turn inward in a subtle way, not toward anything abstract or detached from physics, but towards something that has been quietly present in every part we've discussed so far. Because when we talk about particles, fields, interactions, and even space-time, there is one element that always remains in the background, rarely questioned directly, yet impossible to remove from the picture. And that element is the idea of laws, those consistent rules that govern how everything behaves. In the mainstream understanding, the laws of physics are treated as fundamental. They describe how particles interact, how fields evolve, how forces operate, and how the universe unfolds over time. These laws are expressed mathematically, and their predictive power is extraordinary. From the behavior of subatomic particles to the motion of galaxies, the same underlying principles apply, and this consistency is one of the most remarkable features of the universe. It allows us to understand, to predict, and to build knowledge that holds across vast scales of space and time. But if we slow down and look at this more carefully, a quiet question begins to emerge, one that is not often emphasized in basic discussions. What exactly are these laws? Not how they work, but what they are in a deeper sense. Are they simply descriptions of patterns we observe, or do they have some form of existence independent of observation? Are they fixed and unchanging, or could they themselves emerge from deeper structures? The mainstream view tends to treat laws as foundational, even if their ultimate origin is not fully explained. They are the starting point of our models. We observe regularities in nature. We express those regularities as mathematical relationships, and we test those relationships through experiment. If the predictions hold, the laws are confirmed within that domain. This approach has been incredibly successful, and it remains the backbone of scientific progress. But the deeper question lingers. Why should there be laws at all? Why should the universe follow consistent rules instead of behaving in a completely arbitrary way? And why these specific laws, with these particular constants and symmetries, rather than some entirely different set? Now, it's important to stay grounded here. Physics does not currently provide a definitive answer to these questions. Some approaches attempt to derive known laws from deeper principles, such as symmetry, mathematical consistency, or underlying frameworks that reduce the number of arbitrary inputs. Others explore the possibility that what we call laws may be emergent, arising from more fundamental processes, in a way that mirrors how complex behavior emerges from simple rules in other systems. There is also the idea, explored in some theoretical contexts, that different regions of a larger reality could exhibit different effective laws, with our observable universe being one instance among many. This is sometimes discussed in connection with the concept of a multiverse, though this remains speculative and difficult to test directly. And again, the careful approach is not to accept or reject such ideas outright, but to recognize them as attempts to address a genuine question. Why does reality have the structure it does? When we bring this back to particles, something interesting begins to happen. Because particles do not just exist, they behave according to these laws. Their properties, interactions, and transformations are all governed by consistent rules. So in a sense, particles are not just physical entities. They are also expressions of the laws that define them. Without those laws, the concept of a particle would not have meaning in the way we understand it. This leads to a subtle but important shift in perspective. Instead of thinking of laws as something separate from particles, we begin to see them as deeply intertwined. The behavior of particles reveals the structure of the laws, and the laws define what particles can be. They are two aspects of the same system, not independent layers. And this brings us back once again to the idea of emergence. If particles can emerge from fields, and fields may emerge from deeper structures, then it is natural to ask whether the laws themselves might also emerge from an even more fundamental level. Perhaps the consistency we observe is not imposed from the outside, but arises naturally from the underlying structure of reality, whatever that may be. This idea is still very much an open question, but it aligns with a broader pattern we've seen throughout this exploration. Each time we reach what seems like a foundational layer, we discover that it may be part of a deeper framework. And the deeper we go, the more the distinction between things and rules begins to blur. There is also a quiet connection here to mathematics. The laws of physics are expressed mathematically, and this has led to long-standing questions about the relationship between mathematics and reality. Is mathematics simply a tool we use to describe patterns, or does it reflect something more fundamental about the structure of the universe? Why should abstract mathematical relationships correspond so precisely to physical behavior? Some thinkers have suggested that mathematics might not just describe reality, but in some sense underlie it. Others argue that mathematics is a language, and its effectiveness comes from the way we have developed it to match observed patterns. This debate is far from settled, but it adds another layer to our understanding, because it suggests that the particle world is not just physical, but also deeply mathematical, in a way that goes beyond simple measurement. And as all of this unfolds, the image of particles continues to evolve. They are no longer just building blocks, or even just excitations of fields, but part of a system where laws, structures, and behaviors are all interconnected. The particle is not separate from the rules that govern it. It is an expression of those rules, just as much as it is a physical entity. This realization does not simplify the picture, but it does bring a certain kind of coherence. It suggests that the universe is not a collection of independent pieces held together by external laws, but a unified system where structure and behavior arise together. The consistency we observe is not something added on top of reality. It is woven into the fabric of reality itself. And there is something quietly grounding about that idea. The sense that beneath all the complexity, there is a deep level of order, not necessarily simple or fully understood, but consistent and reliable. The laws do not change from moment to moment. The patterns hold. The same interactions produce the same results, again and again, across the vast expanse of the universe. So as you let this settle, the focus shifts once more. Particles are still central to the story, but they are no longer the only focus. They are part of a larger system that includes laws, structures, and relationships, all of which work together to produce the reality we experience. And perhaps the most interesting part is not just what these laws are, but the possibility that they too are part of a deeper story. One that we are only beginning to glimpse, layer by layer, as we continue to look more closely at the smallest things. As we continue deeper into this slow unraveling, there is a point where the conversation becomes almost deceptively simple again, as if everything we've explored begins to circle back to something familiar, but now seen from a slightly different angle. Because after examining particles, fields, space-time, relationships, and even the laws themselves, another quiet question begins to emerge, one that sits at the intersection of all of these layers. If everything is built from the same underlying rules and structures, why does the universe feel so directional, so one way? In everyday life, time seems to move forward with complete certainty. You remember the past, but not the future. Causes lead to effects, not the other way around. Objects age, systems evolve, and processes unfold in a clear direction. This forward flow feels so natural that it rarely invites questioning. But when we look at the level of particles, something unusual happens. The fundamental equations that describe their behavior often do not strongly prefer a direction of time at all. In many cases, the laws of physics work just as well if time is reversed. The same interactions, the same probabilities, the same mathematical structure can describe processes moving backward just as consistently as forward. This symmetry is not universal. There are small violations in certain particle interactions, but for the most part, the underlying rules do not impose a clear arrow of time. And this creates a quiet tension, because if the laws governing particles are mostly time-symmetric, then where does the strong sense of time flowing in one direction come from? Why does the world not feel reversible at every scale? The mainstream explanation points toward thermodynamics, specifically the concept of entropy. Entropy is often described as a measure of disorder, though a more precise way to think about it is as the number of possible configurations a system can have. Systems naturally evolve from less probable states to more probable ones. A neat arrangement of particles tends to spread out into a more mixed, less ordered state, simply because there are far more ways for things to be disordered than ordered. This statistical tendency gives rise to what we call the arrow of time. As entropy increases, processes appear to move forward. A glass can fall and shatter, spreading its pieces across the floor, but the reverse process, those pieces spontaneously reassembling into a glass, is so extraordinarily unlikely that it effectively never happens. And so, at the level of everyday experience, time feels irreversible. But if we return to the particle level, the picture becomes more nuanced. Individual interactions do not necessarily know about the arrow of time in the way large systems do. The directionality emerges when we consider vast numbers of particles interacting together, producing statistical patterns that give rise to the flow we experience. And this leads to a subtle but important realization. The arrow of time may not be a fundamental feature of the smallest components of reality, but an emergent property of large systems. In other words, time as we experience it may arise from the collective behavior of particles, rather than being something built into each particle individually. This idea fits into the broader pattern we've been exploring. Once again, something that feels fundamental at our scale turns out to be emergent at a deeper level. Just as solidity emerges from interactions and individuality emerges from patterns, the flow of time itself may emerge from statistical behavior. But this opens the door to another quiet question. If time's direction is not deeply embedded in the smallest laws, then what does that say about the nature of those laws? Are they operating in a framework where past and future are, in some sense, equally valid descriptions? And if so, what does it mean for particles to exist in time at all? Now, the grounded approach is to avoid jumping to dramatic conclusions. Physics does not claim that time is an illusion in the everyday sense. Processes still unfold, and causality still operates reliably at observable scales. But it does suggest that the deeper structure of reality may not align perfectly with our intuitive sense of temporal flow. There are even interpretations and theoretical frameworks where time is treated not as a fundamental dimension, but as something that arises from more basic relationships. In these views, the sequence of events we experience may be a way of organizing information about interactions rather than a built-in feature of the underlying system. And again, this is not settled science. It is an area of active research and debate, with many competing ideas and no single agreed-upon answer. But it adds another layer to our understanding of particles, because it suggests that particles are not just existing in time as we perceive it, but may be part of a structure where time itself is a secondary feature. There is also an interesting connection here to measurement and observation. When we measure a particle, we record an outcome at a specific moment. We place that outcome within a timeline, connecting it to past measurements and future predictions. But the equations describing the particle's behavior often extend beyond that single moment, encompassing a range of possibilities that are not confined to a single point in time in the way our observations are. This creates a kind of dual perspective. On one hand, we have the clear, ordered sequence of events we observe and record. On the other hand, we have the underlying mathematical description, which does not always prioritize that sequence in the same way. And the relationship between these two perspectives is still not fully understood. As all of this settles in, the concept of a particle becomes even more subtle. It is no longer just a localized excitation or a relational event, but something that participates in a system where even time may not be as straightforward as it appears. The particle exists, interacts, and evolves, but the framework in which these processes occur may be more flexible, more layered than our everyday experience suggests. And there is something quietly profound about that. The idea that the flow of time, which feels so immediate and undeniable, may itself be a product of deeper processes. That beneath the steady forward movement we experience, there may be a level of reality where direction is not as fixed, where past and future are part of a broader structure we are only beginning to understand. But rather than making the world feel uncertain, this perspective can have the opposite effect. It highlights the stability of the patterns we do observe. The arrow of time may emerge from statistical behavior, but it is remarkably consistent at our scale. The processes that shape our lives follow clear, reliable paths, even if their foundation is more subtle. So as you sit with this idea, letting it unfold without forcing it into a conclusion, you begin to see particles not just as components of matter, but as participants in a system where time, like so many other features, may emerge from deeper layers of structure. And that realization, gentle as it is, adds another dimension to the quiet mystery we've been exploring. A reminder that even the most familiar aspects of reality may have origins that are still waiting to be fully understood. As we continue, something begins to settle into place, not as a final answer, but as a kind of quiet alignment between everything we've explored so far. Particles, fields, interactions, space-time, laws, information, time itself. Each layer has slowly softened the idea that reality is built from simple, solid pieces. And now, as we move further, another question begins to rise naturally from all of this, almost like a whisper rather than a statement. If the foundation of reality is this fluid, this relational, this structured yet open, then what, if anything, is truly fundamental? Because up to this point, each time we've approached what seems like a base layer, it has shifted. Particles lead to fields. Fields raise questions about deeper structures. Space may emerge from relationships. Time may emerge from statistical behavior. Laws themselves may not be as fixed or independent as they first appear. And this pattern, this repeated uncovering of deeper layers, begins to suggest something subtle but important. Not necessarily that there is no foundation, but that the foundation may not be a thing in the way we usually imagine. The mainstream perspective still holds that there is some fundamental structure, even if we have not fully described it yet. Physics continues to search for a unified framework, something that can reconcile quantum mechanics with gravity, explain the constants of nature, and reduce the number of assumptions needed to describe reality. This search is ongoing, careful, and grounded in evidence. It does not assume that the foundation is unreachable, only that it has not yet been fully uncovered. But alongside this effort, there is another way of looking at the pattern we've been tracing, a more observational approach rather than a conclusive one. And it simply asks, what if the idea of a single, final layer is itself a kind of simplification? What if reality is not built like a stack with a clear bottom, but more like a network, where each layer depends on others, and the concept of most fundamental becomes less absolute? This idea does not reject the search for deeper understanding, it reframes it. Instead of expecting a single ultimate building block, it allows for the possibility that reality is structured in a way where different aspects, particles, fields, space-time, information, are all part of a tightly interconnected system, none of which can be fully understood in isolation. And interestingly, this kind of thinking has begun to appear, quietly, in some areas of modern physics. Not as a replacement for existing theories, but as a way of interpreting how those theories fit together. The focus shifts from finding the smallest object to understanding the relationships that give rise to everything we observe. Because if you look back at everything we've discussed, one theme keeps returning. Not objects, but relationships. Not isolated things, but interactions. Not fixed properties, but context-dependent outcomes. And this pattern is consistent enough that it begins to feel less like a collection of coincidences and more like a hint about the structure of reality itself. Now, again, we stay grounded. This is not a conclusion. It is a way of noticing what the current understanding seems to point toward. The Standard Model, quantum mechanics, relativity, all of them remain incredibly successful within their domains. They do not need to be replaced to ask these deeper questions. They provide the foundation from which these questions arise. But the questions themselves are worth holding, because they shift the focus from what is the smallest thing to how does the system hold together at every level. And that shift changes how we think about particles. Particles, in this light, are no longer candidates for the final layer of reality. They are part of a dynamic system that expresses itself in different ways at different scales. They are stable enough to build matter, predictable enough to be measured, and consistent enough to form the basis of physical law. But they are also flexible enough to behave as waves, to exist in superpositions, to become entangled, to emerge from fields, and possibly to participate in structures that extend beyond our current models. There is also something quietly revealing about how particles are discovered in the first place. We do not observe them directly in the way we observe everyday objects. We infer their existence through interactions, through traces, through patterns in detectors. A particle appears as a result, a signal, a measurement, an event. This reinforces the idea that particles are not simply there in a classical sense, waiting to be seen, but are part of processes that become visible under certain conditions. And this brings us back, once more, to a familiar but now deeper realization. The more closely we examine reality, the more it seems to resist being described in terms of static, independent pieces. Instead, it reveals itself as a system of ongoing activity, where stability and change, order and uncertainty, all coexist within a framework that is precise but not fully resolved. There is also a certain elegance in this, the idea that reality does not reduce to a single, simple component, but instead unfolds through layers of structure that connect and depend on one another. It suggests that understanding the universe is not about reaching an endpoint, but about exploring how these layers relate, how they support each other, how they give rise to the patterns we observe. And perhaps this is why the search continues. Not because the current models are failing, but because they are working so well that they reveal their own boundaries. They point toward deeper questions simply by being so precise within their range. So as you let this settle, there is no need to resolve it into a final answer. The question of what is truly fundamental remains open, and that openness is not a weakness. It is part of the structure of the inquiry itself. Particles remain central to the story, but they are no longer the end of it. They are part of a larger, more intricate system, one that we are still learning to describe, still learning to understand, and perhaps still learning how to even think about in the most accurate way. And as that thought gently fades into the background, what remains is not uncertainty in a restless sense, but a kind of quiet clarity. The recognition that reality, even at its smallest scales, is not closed or finished, but still unfolding, still offering new layers to explore. As we continue, the tone shifts once again, but this time in a way that feels almost reflective, as if everything we've explored so far is beginning to turn back on itself, not to repeat, but to deepen. Because after moving through particles, fields, space, time, laws, and emergence, there is one more layer that quietly waits beneath all of it. A question that is less about what reality is made of and more about how we come to understand it at all. Because every description we've discussed, every model, every equation, every interpretation is something constructed within human understanding, not in the sense that reality depends on us, but in the sense that our access to reality is always filtered through the ways we measure, interpret, and describe what we observe. And this raises a subtle but important point. The story of particles is not just a story about the universe. It is also a story about the limits and strengths of human knowledge. The mainstream scientific approach is built on observation, measurement, and repeatability. It does not claim absolute final truth in a philosophical sense. Instead, it builds models that describe behavior with increasing accuracy, refining them as new data becomes available. This approach has been extraordinarily successful, allowing us to uncover the structure of atoms, predict the existence of particles before they are observed, and understand interactions at scales far beyond direct perception. But even within this success, there is an implicit boundary. Our models describe how systems behave under specific conditions, using concepts and mathematics that make sense within our framework of understanding. They are maps of reality, not reality itself. And the closer we look at particles, the more we begin to notice the edges of those maps. For example, the wave function in quantum mechanics is a central tool for describing particle behavior. It evolves according to precise equations and produces predictions that match experiments with remarkable accuracy. But what the wave function actually represents is still debated. Is it a real physical entity, something that exists independently of observation? Or is it a mathematical construct that encodes our knowledge of a system? Different interpretations offer different answers, and the fact that these interpretations coexist without changing experimental predictions suggests that the underlying reality may not be fully captured by any single description. This is not a flaw in physics. It is a reflection of the depth of the subject. When dealing with systems that operate far beyond everyday experience, it is not surprising that our conceptual tools begin to stretch. And rather than forcing a single interpretation, physics allows multiple perspectives to coexist, as long as they remain consistent with observed data. This leads to a quiet, but meaningful realization. The particle story is not just about uncovering what is out there. It is also about refining how we think, how we describe, how we make sense of phenomena that do not fit easily into intuitive categories. In this sense, the study of particles becomes as much about expanding understanding as it is about discovering facts. There is also a subtle interplay between simplicity and complexity in this process. On one hand, the fundamental laws governing particles are expressed in elegant mathematical forms. On the other hand, the behavior that emerges from those laws can be incredibly complex, especially when large numbers of particles interact. This duality, simple rules leading to complex outcomes, is a recurring theme in many areas of science, but it is particularly striking in particle physics. And it raises another question. When we seek to understand particles, are we trying to simplify reality down to its most basic components, or are we trying to understand how complexity arises from those components? The answer, of course, is both. But the balance between these two goals shapes how we approach the subject. If we focus only on reduction, we risk overlooking the importance of relationships, interactions, and emergent properties. If we focus only on complexity, we risk losing sight of the underlying simplicity that makes the system understandable. And so, the study of particles becomes a kind of balancing act, moving between these perspectives, adjusting as new insights emerge. There is also the question of language. The words we use, particle, wave, field, interaction, are attempts to describe phenomena that do not always fit neatly into everyday categories. A particle is not quite a particle in the classical sense. A wave is not quite a wave in the familiar sense. These terms are approximations, chosen because they capture certain aspects of behavior, but they are not complete descriptions. This is why physics relies so heavily on mathematics. Mathematical language can describe relationships and patterns with a level of precision that ordinary language cannot. But even mathematics has its limits. It can model behavior, but interpreting what those models mean in a deeper sense often requires stepping beyond the equations into conceptual territory that is less clearly defined. And this brings us back to the idea of interpretation. Throughout the history of physics, different interpretations have coexisted, sometimes competing, sometimes complementing each other. In quantum mechanics, this is especially evident. The equations are agreed upon. The predictions are consistent. But the meaning of those equations is still open to discussion. This openness is not a weakness. It is a sign that the subject is still evolving. It suggests that our current understanding, while powerful, may not yet be complete. And it invites a certain kind of humility in how we approach the topic. Not a passive humility, but an active one. A willingness to explore, to question, to refine, without rushing to closure. Because in a field where the smallest components of reality behave in ways that challenge intuition, it is reasonable to expect that our understanding will continue to evolve. And as this realization settles, something else begins to emerge. A sense that the search itself is part of the structure we are trying to understand. The act of observing, measuring, modeling, and interpreting is not separate from the universe. It is a process happening within it. Our efforts to understand particles are themselves physical processes, governed by the same laws we are trying to uncover. This does not blur the line between observer and reality in a confusing way. It simply places our understanding within the system, rather than outside of it. And in doing so, it highlights the continuity between what we study and how we study it. So as you let this final layer of Part 11 settle in, the picture becomes a little more complete, not in the sense of being finished, but in the sense of being more fully connected. Particles are part of a system. Laws are part of that system. Space, time, and interaction are part of that system. And our understanding of all of it is also part of that system. And perhaps the most calming realization in all of this is that the mystery is not something separate from the knowledge. It is woven into it. The more we understand, the more clearly we see where understanding ends and deeper questions begin. And that boundary, rather than being a limit, becomes a place of quiet curiosity, a place where the exploration continues without urgency, without final answers, but with a steady sense that there is always more to see. As we continue, there is a noticeable softening in the way the entire subject begins to feel, as if the deeper we go, the less it becomes about solving something, and the more it becomes about sitting with a pattern that is slowly revealing itself. Not all at once, not dramatically, but in layers that connect more than they conclude. And at this point in the journey, another quiet idea begins to surface, one that has been present in fragments throughout everything we've discussed, but now comes into focus more clearly. The possibility that what we call reality is not just structured, but encoded in a way that we are only beginning to recognize. Now, to stay grounded, we begin with what is firmly established. In modern physics, information has become an increasingly important concept, not as a replacement for matter or energy, but as a way of describing how physical systems are organized and how they evolve. When a particle has a certain state, that state can be described as information. When particles interact, they exchange and transform information, When a system changes over time, what we are really tracking, in a precise sense, is how information moves and reorganizes within that system. This is not speculative language. It is part of how quantum theory is currently framed, especially in areas like quantum information theory. For example, when two particles become entangled, their combined state contains information that cannot be reduced to either particle alone. The system must be described as a whole. And when measurements are made, information about the system becomes encoded in the measuring device, the environment, and ultimately in any record of the observation. So already, within mainstream physics, there is a shift from thinking purely in terms of things to thinking in terms of states and information. And this shift, while subtle, opens the door to deeper questions. Because once you begin to describe particles in terms of information, it becomes natural to ask, is information just a way of describing reality, or is it something more fundamental? Are particles carriers of information, or are they themselves expressions of underlying informational structures? Some physicists have explored the idea that information might be one of the most basic ingredients of the universe. Not in the sense of digital bits stored on a computer, but in a more abstract sense, patterns, distinctions, relationships that define the possible states of a system. In this view, matter and energy are ways that information manifests under certain conditions. Again, this is not a universally accepted conclusion. It is an area of exploration with different interpretations and ongoing debate. But it aligns with the pattern we've been tracing. Each time we look deeper, we find that what seemed like a solid object becomes a process, and what seemed like a process becomes a structure of relationships. And now, those relationships can be described in terms of information. And this leads to a very quiet but powerful question. If reality can be described in terms of information, then where is that information stored? Is it located in space, in particles, in fields, or is it something more distributed, something that exists as part of the system as a whole? The mainstream answer would be cautious. Information is not stored in a single place in the way we might imagine. It is encoded in the state of the system. It exists in the relationships between components, in the configuration of fields, in the outcomes of interactions. It is not a separate substance, but a way of describing the structure of what exists. But even with that careful framing, something interesting remains. Because if information is tied to the state of the system, and if that state evolves according to physical laws, then the entire universe can be seen, in some sense, as a process of information unfolding over time. Not in a metaphorical sense, but in a very literal, measurable way. And this connects to another idea that has been explored in theoretical physics, that the total amount of information in a system may be conserved, even as it changes form. This is a complex topic, especially when it comes to things like black holes, where information appears to be lost, but deeper analysis suggests it may be preserved in ways that are not immediately obvious. The details are still being worked out, but the principle itself, that information plays a fundamental role in physical processes, has become increasingly central. Now, as always, we avoid jumping ahead. The idea that reality is made of information is not a settled conclusion. It is one possible way of interpreting a growing body of evidence. But even without fully adopting that perspective, it is clear that information is not just a secondary concept. It is deeply woven into how particles behave and how systems evolve. And this brings us back to the idea of particles, but now with a slightly different lens. Instead of thinking of a particle as a tiny object, or even just as a ripple in a field, we can begin to think of it as a localized expression of information. A point where certain possibilities are realized, where certain relationships take on a specific form, where the abstract becomes concrete in a measurable way. This does not replace the existing models. It complements them. It adds another layer of understanding, another way of looking at the same behavior. And like everything else we've explored, it raises new questions even as it clarifies old ones. There is also something quietly unifying about this perspective, because information does not belong to one scale or another. It applies to particles, to atoms, to biological systems, to entire galaxies. It provides a common language that can describe patterns across different levels of complexity. And this suggests that the same underlying principles may be at work throughout the universe, expressed in different forms at different scales. And once again, the theme of emergence returns. Information at one level gives rise to structure at another. Simple patterns combine into more complex ones. Relationships build on relationships, creating layers of organization that appear distinct, but are connected at a deeper level. So as you let this idea settle, gently and without forcing it into a final shape, the picture of particles becomes even more fluid. They are not just physical entities, not just excitations, not just relational events, but also carriers and expressions of information within a system that is constantly evolving. And that system, rather than being static or fully defined, remains open, structured, consistent, but still revealing new layers as we look more closely. And perhaps that is the quiet thread running through all of this. Not a single answer, but a pattern of discovery. A sense that the deeper we go, the more the universe reveals itself, not as something rigid and final, but as something dynamic, interconnected, and still, in many ways, unfolding. As we continue, there is a sense now that everything we've explored is beginning to gently converge, not into a final answer, but into a clearer outline of the mystery itself. And at this stage, something subtle but deeply important begins to emerge from the background of all these ideas. Something that has been implied in different ways throughout our journey, but now becomes more visible. The possibility that reality, at its deepest level, may not be something we can fully separate into independent parts at all. Because if we step back and look at the pattern that has unfolded, it becomes difficult to ignore. Particles are not truly independent objects. They are excitations of fields. Fields themselves may arise from deeper structures. Space may emerge from relationships. Time may emerge from statistical behavior. Laws may be expressions of underlying consistency rather than external rules. Information may describe the structure of everything we observe, and at every step, the idea of separateness becomes less absolute. The mainstream scientific view does not deny connection. In fact, it relies on it. Interactions, correlations, and shared states are central to how particles behave. But traditionally, these connections are described within a framework where objects still exist as distinct entities that interact across space. And that framework works extremely well for making predictions and building models. But when we follow the implications of quantum behavior closely, especially entanglement, indistinguishability, and the relational nature of properties, a different perspective begins to quietly form. One where the separation between objects is not the starting point, but something that emerges under certain conditions. In this view, what we perceive as distinct things may be stable patterns within a system that is fundamentally unified at a deeper level. Now, again, we stay grounded. This is not a claim that everything is literally one thing in a simplistic or mystical sense. Physics does not make that statement. What it does show is that the boundaries we perceive between particles, between objects, even between regions of space, are not as rigid at the fundamental level as they appear at larger scales. And this leads to a very quiet but powerful shift in perspective. Instead of asking how separate things connect, we begin to ask how apparent separation arises from a more interconnected foundation. This idea becomes especially interesting when we revisit entanglement. When two particles are entangled, their combined state cannot be described independently. The system must be treated as a whole. And while this does not allow for faster-than-light communication, it does show that the properties of the system are not localized in the way we might expect. If we extend this idea carefully, not as a conclusion, but as a question, it suggests that the universe itself may not be fully decomposable into independent parts. That the division into separate systems is, in some sense, an approximation that works at certain scales, but not necessarily at the deepest level. And this aligns with another pattern we've seen: emergence. At larger scales, separation becomes meaningful. Objects form, boundaries stabilize, individuality appears. But these features may arise from underlying processes that are more interconnected than our everyday experience suggests. There is also a subtle connection here to how we define systems in physics. When studying a particle, we often isolate it, treat it as a system, and analyze its behavior under controlled conditions. But in reality, no system is ever completely isolated. There are always interactions, always connections, even if they are small or difficult to detect. This means that the idea of a perfectly independent particle is, in practice, an approximation. A useful one, but still an approximation. And the more precisely we look, the more those approximations begin to reveal their limits. Another layer to this discussion involves scale once again. At the quantum level, interconnectedness is more visible, more direct. At larger scales, the complexity of interactions makes systems appear more independent. This is not because the connections disappear, but because they become averaged out, stabilized into patterns that behave predictably. So once again, the theme returns. What we experience as solid, separate, and stable may be an emergent feature of a deeper, more fluid system. And there is something quietly reassuring about that. Not because it simplifies the universe, but because it suggests that the apparent complexity and fragmentation of the world may rest on a more unified foundation. That beneath the countless forms and structures, there is a coherence that holds everything together, even if we do not yet fully understand how. This does not remove the distinctions we experience. It does not erase individuality or structure. It places them within a broader context, where separation is not absolute, but relative, dependent on scale, interaction, and perspective. And as you let that idea settle, gently and without forcing it into a conclusion, the concept of particles becomes almost secondary. Not unimportant, but no longer the central focus. They are part of the story, but the story itself is larger, about relationships, about structure, about the way reality organizes itself across different levels. And perhaps that is where the calmness of this exploration comes from. Not from resolving the mystery, but from recognizing its shape. The sense that the deeper we go, the more the universe reveals a kind of quiet consistency, not in the form of simple answers, but in the way each layer connects to the next. So as we rest here, at this point in the journey, there is no need to decide what the final picture looks like. The important thing is the pattern we've uncovered, the recurring theme of connection, emergence, and depth, and the understanding that particles, as small as they are not isolated fragments of reality, but part of something far more continuous, far more interconnected, and still, in many ways, waiting to be understood. As we continue, there is a feeling now that the exploration is beginning to slow, not because there is less to say, but because the nature of what we are examining becomes quieter, more subtle, less about uncovering new pieces, and more about seeing how everything we've already uncovered fits together. And at this stage, one of the most intriguing realizations begins to settle in, almost gently. The possibility that the deepest secrets of particles are not hidden in complexity, but in how deceptively simple the underlying patterns might be. Because if we trace the entire path we've taken so far, something becomes clear. The behavior of particles, while strange, is not chaotic. It follows precise mathematical rules. It produces consistent outcomes. It builds stable structures. And even the most unusual features, uncertainty, entanglement, superposition, are not random in the sense of being without structure. They are governed by well-defined principles that hold across every experiment we can perform. This raises a quiet but powerful question. If the universe operates with such consistency at its deepest levels, then why does it appear so complex at larger scales? Why does a system built from relatively simple rules give rise to such an enormous range of structures, behaviors, and phenomena? The mainstream answer points, once again, to emergence. Simple underlying rules can generate complex outcomes when applied repeatedly across many interacting components. This is not unique to particle physics. It appears in many systems, from fluid dynamics to biological processes to patterns in nature. But in the context of particles, it becomes especially striking because the simplicity of the fundamental laws contrasts so strongly with the richness of the world they produce. And this leads to an interesting shift in perspective. Instead of viewing particles as mysterious because they are complicated, we begin to see them as mysterious because they are part of a system where simplicity gives rise to complexity in ways that are not always intuitive. There is also something else worth noticing here. The equations that describe particle behavior are often remarkably elegant. They rely on symmetry, consistency, and mathematical relationships that are, in many cases, surprisingly concise given the vast range of phenomena they explain. This has led some physicists to wonder whether elegance itself might be a clue, whether the simplicity of the underlying rules reflects something fundamental about the structure of reality. Now again, we stay grounded. Elegance in mathematics does not guarantee truth. It is a guide, not a proof. But the recurring appearance of simple, consistent patterns at the foundation of complex systems is difficult to ignore. It suggests that the complexity we observe may not be rooted in complicated rules, but in the way simple rules interact over time and across scales. And this brings us back to particles, but now with a different kind of clarity. They are not complicated objects in themselves. Their behavior can be described with precision. What makes them feel mysterious is the way they fit into a larger system that is layered, interconnected, and still not fully understood. There is also a quiet implication here about predictability. At the level of individual particles, outcomes can be probabilistic. We can predict the likelihood of different results, but not always the exact outcome of a single event. But as we move to larger systems, predictability increases. Patterns stabilize. Behavior becomes more deterministic in practice, even if the underlying processes remain probabilistic. This transition, from uncertainty at small scales to stability at large scales, is one of the most important features of the particle world. It allows a universe built on probabilities to produce reliable structures. It allows randomness to coexist with order. And it shows, once again, how different layers of reality can exhibit different characteristics while still being part of the same system. Another aspect of this simplicity is the repetition of patterns. The same types of particles appear everywhere. The same interactions occur under the same conditions. The same structures form across vast distances. This repetition is not just a convenience. It is a fundamental feature of how the universe operates. And it raises a quiet question. Why should the universe be so consistent? Why should the same patterns repeat with such precision across space and time? The mainstream answer is that the laws of physics are uniform, and that uniformity produces consistent outcomes. But the deeper reason for that uniformity remains an open question. there is also something almost paradoxical about this. The universe is both incredibly simple and incredibly complex at the same time. Simple in its underlying rules, complex in its outcomes. Predictable in its patterns, unpredictable in its individual events, stable in its large-scale structures, dynamic at its smallest scales. And particles sit right at the center of this balance. They are where the simplicity of the laws meets the complexity of the world. They are the point where abstract rules become tangible, where mathematical relationships become physical events. As we let this settle, the idea of secrets begins to shift once more. It becomes less about hidden information waiting to be uncovered, and more about recognizing patterns that are already there, but not always seen clearly. The mystery is not that the rules are complicated, but that their implications are so far-reaching. And this leads to a kind of quiet clarity. The realization that understanding particles is not just about looking deeper, but about seeing more clearly, about recognizing how simple principles can give rise to a universe that feels almost endlessly complex. There is no need to resolve this into a final answer. The balance between simplicity and complexity is not something to be solved, but something to be observed. It is part of the structure of reality itself. So as you sit with this idea, letting it unfold gently, you begin to see particles not as isolated puzzles, but as part of a system where simplicity and complexity are woven together in a way that is both precise and still not fully understood. And that realization, quiet as it is, brings us closer to the heart of the subject, not a conclusion, but a clearer sense of the pattern that holds everything together. As we continue, there is a noticeable stillness that begins to settle over everything we've explored, as if the questions themselves are no longer pushing forward, but instead gently circling back, revealing the same ideas from slightly different angles, each time with a little more clarity. And at this stage, something almost unexpected begins to emerge. Not a new concept, but a new way of seeing what has been there all along. Because after examining particles from so many perspectives, objects, waves, excitations, relationships, information, patterns, one realization begins to quietly stand out above the rest. Not as a dramatic conclusion, but as a kind of quiet alignment, that the deeper we look, the less reality seems to depend on any single definition. A particle is not just a particle. It is not just a wave, not just a field excitation, not just a unit of information, not just a relational event. It is all of these descriptions, depending on how we look, how we measure, and what aspect of its behavior we are focusing on. And none of these descriptions are wrong. They are each accurate within their context, but none of them, on their own, seem to fully capture the whole picture. The mainstream scientific view acknowledges this in a practical sense. Different models are used for different purposes. Quantum mechanics provides one framework, quantum field theory another, relativity another. Each one works within its domain, producing reliable predictions and consistent results. The challenge is not that these models fail, but that they do not always merge into a single, unified description that feels complete at every level. And so, what we are left with is not a contradiction, but a kind of layered understanding. Reality can be described in multiple ways, each revealing certain features while leaving others less defined. And particles sit right at the center of this layered picture, where different descriptions overlap. This leads to a subtle but important shift. Instead of asking which description is the correct one, we begin to ask how these descriptions relate to each other. How does the wave-like behavior connect to the particle-like behavior? How do fields give rise to particles? How do interactions produce stable outcomes? These are not questions about replacing one model with another, but about understanding how they fit together. And this is where the tone of the exploration becomes especially calm. because it moves away from the idea that there must be a single, final answer waiting at the bottom. Instead, it allows for the possibility that understanding may come from seeing how multiple perspectives align, rather than reducing everything to one. There is also something quietly reassuring about this. The idea that reality does not collapse into a single rigid definition, but instead allows for multiple consistent descriptions, suggests a kind of flexibility at the foundation of the universe. Not chaos, not contradiction, but a system that can be approached from different angles, each revealing part of the structure. And this flexibility is reflected in the behavior of particles themselves. They adapt to the context of measurement. They exhibit different properties under different conditions. They are not locked into a single mode of existence, but instead exist within a range of possibilities that become defined through interaction. This does not make them less real, it makes them more nuanced. It shows that reality, at its smallest scales, is not limited to the categories we use at larger scales. It operates according to rules that allow for a broader range of behavior than our everyday intuition might suggest. There is also a connection here to the limits of language. The words we use, particle, wave, field, are tools, not final definitions. They help us describe what we observe, but they do not fully capture the underlying reality. And as we push further into the details, we begin to see where those words start to stretch, where they remain useful but incomplete. This is why the exploration has taken on the tone it has, not rushing toward conclusions, not forcing clarity where it does not yet exist, but allowing the ideas to unfold gradually, each one adding to the picture without closing it. And now, as we approach the later stages of this journey, the focus begins to shift once more, not toward a final answer, but toward a kind of acceptance. Not acceptance in the sense of giving up on understanding, but in the sense of recognizing that understanding itself may not take the form we expect. Because perhaps the most important insight is not what particles are, but how they challenge the way we think about what something is at all. They show that reality can be consistent without being simple, structured without being rigid, understandable without being fully reducible. And there is something deeply calming in that realization. The sense that the universe does not need to be forced into a single, final picture to be meaningful. That it can be explored, described, and understood in layers, each one adding depth rather than replacing what came before. So as you sit with this, letting the ideas settle into a kind of quiet coherence, the concept of particles becomes less about definition and more about perspective. They are not a single answer, but a point where many answers meet. And that, in its own way, feels like a kind of resolution, not because it closes the question, but because it shows how the question itself can be held without needing to be solved completely. As we arrive here, at the final part of this long and quiet exploration, there is a natural inclination to look for a conclusion, to gather everything we've discussed and compress it into a single clear answer about what particles truly are, what their secrets ultimately reveal, and where all of this leads. But something subtle has been building throughout this journey, something that gently resists that kind of ending. Because the deeper we've gone, the more it has become clear that the story of particles is not one that closes neatly, not because it is incomplete in a frustrating way, but because it is structured in a way that continues to open. Each layer we've explored has added clarity, but also depth. Each answer has revealed a little more of the pattern, but also shown where that pattern extends beyond the edge of what we can currently define. And perhaps that, in itself, is the most honest place to arrive. If we return to the beginning, to the simple idea that particles are the smallest building blocks of reality, we can now see how much that idea has evolved. Particles are not solid objects in the classical sense. They are not isolated units moving through empty space. They are excitations of fields, expressions of interactions, participants in systems that are relational, probabilistic, and deeply structured. We've seen how their behavior is governed by laws that are precise, yet not fully explained at their deepest level. How their properties emerge through interaction rather than existing independently in a fixed way. How their indistinguishability challenges our sense of individuality. How their entanglement suggests connections that are not easily described in terms of distance. How space and time themselves may not be as fundamental as they appear. And how information may play a role that we are only beginning to understand. And through all of this, one pattern has remained consistent. Not a single answer, but a shift in perspective. A movement away from thinking of reality as a collection of separate things, towards seeing it as a system of relationships, patterns, and structures that reveal themselves differently at different scales. The mainstream scientific view remains firmly grounded. The Standard Model continues to describe particle behavior with extraordinary accuracy. Quantum mechanics continues to predict outcomes that match experiment with remarkable precision. Relativity continues to explain the structure of space-time on cosmic scales. These are not uncertain or fragile frameworks. They are among the most successful achievements of human understanding. But alongside that success, there is an openness, an awareness that these models, as powerful as they are, may not yet be the final layer. That there are still questions about unification, about the nature of fields, about the origin of laws, about the role of information, about the emergence of space and time. And rather than seeing those open questions as gaps to be filled as quickly as possible, there is value in simply recognizing them, in allowing them to exist without forcing them into premature conclusions. Because the deeper lesson of the particle world may not be about finding a final answer at all. It may be about learning how to navigate a system where answers and questions are part of the same structure. Where understanding grows not by closing off possibilities, but by refining how we ask, how we observe, how we connect ideas across different layers. There is also something quietly grounding about the consistency we've seen. Despite all the subtlety, all the nuance, all the open questions, the universe behaves in reliable ways. The same interactions produce the same results. The same patterns repeat across space and time. The same underlying rules hold, even as we continue to explore their deeper meaning. So there is no instability here. No sense that reality is slipping away from understanding. Only the recognition that understanding itself is layered. That clarity at one level does not eliminate mystery at another. And perhaps that is where the calmness of this entire exploration comes from. Not from resolving the mystery, but from seeing its shape clearly enough to know that it does not need to be resolved all at once. Particles, in the end, are not just the smallest pieces of the universe. They are entry points into a deeper way of thinking about reality. They show us that certainty and uncertainty can coexist. That simplicity and complexity can emerge from the same foundation. That separation and connection are not opposites, but different aspects of the same system. And maybe most importantly, they remind us that the universe is not something fully finished and sealed off from understanding, but something that continues to reveal itself gradually, in ways that reward patience, curiosity, and careful observation. So as this journey comes to a close, there is no final statement to hold on to, no single definition to carry forward, only a quieter awareness that the smallest things we know about are not simple, that the deeper we look, the more interconnected everything appears, and that the search for understanding, much like the particles themselves, is not a fixed point, but an ongoing process, one that continues even after we stop looking directly. And maybe that's enough for now.